even after controlling for age. The coefficient of age, 1.678, is talking about old people versus young people, controlling for sex. So this is the way we can control for confounders through a model. And notice in this case, if I go back, I get essentially the same number, 2.04, with essentially the same confidence interval, 1.55 to 2.68, that I had when I did stratification. If I go back to the stratified analysis, the coefficient was 2.04. The confidence interval went from 1.55 to 2.68. Now if I go to the model, I get essentially the same adjusted odds ratio, essentially the same confidence interval. So again, what I could do for controlling confounding through stratification, I can do the same thing with a model by including a term in the model for the types of confounders. So let's suppose I have a continuous confounder, like age. What I did in the previous example is I categorized it, because that's what I had to do if I did a stratified analysis. So my model was essentially the same as a stratified analysis. But I have another option. I don't have to categorize age to control for it in a model. I can control for it as a single term. So for example, last week we looked at smoking in two different ways. As a categorical variable, Pax 1 represented a 1-pack-a-day smoker, Pax 2 a 2-pack-a-day smoker, Pax 3 was a 3-pack-a-day smoker. What this model is doing is controlling for smoking. Look at the effect of male versus females. And it's the way it's controlling for smoking is by breaking it into categories. Non-smokers, 1-pack-a-day smokers, 2-pack-a-day smokers, 3-pack-a-day smokers. This is similar to stratifying by smoking after I categorized it into 4 groups. Non-smokers, 1-pack-a-day smokers, 2-pack-a-day smokers, or 3-pack-a-day smokers. The adjusted coefficient of sex becomes an odds ratio of 1.97, meaning that controlling for smoking as a categorical variable, this model says males have 1.97 odds of getting disease compared to females. But another way I could do it is I could control for smoking as a single variable, Pax. Now, as I mentioned last week, what that means is I'm making an assumption of linearity. Essentially, what I'm assuming is the following picture, that the males and the females have their risk of getting, or their log odds of getting disease, it depends on their smoking status. It depends on it in a certain way. The model assumes that smoking has a linear relationship. Go back to the previous slide. If I look at females, their value for male would equal 0. So their log odds of disease becomes minus 1.79 plus 0.0451 times their level of smoking. That's an equation of a straight line. That means females have a straight line with an intercept equal to, in the previous slide, minus 1.9723 and a slope of 0.0451. Males, on the other hand, have a value of 1 for male. So their model becomes minus 1.79 plus 0.68, which is like a minus 1.1, plus 0.04 times their smoking level. So they have another line with the same slope, but a different intercept. So what that model that we just looked at is assuming is that smoking has a linear effect on your risk of developing, on your log odds of developing coronary heart disease. And females and males both have a different effect because it shows the difference or the gap between these two straight lines. Male's line is a fixed distance above the line of a female. It says for any level of smoking, if you compare a male to a female at that level, we'd be comparing 2 points on 2 different. How much higher the male's log odds of disease is compared to a female. Well, that's what this number 0.6838 is. It's the gap between those two lines. We know mathematically that's the log odds ratio. That corresponds to an odds ratio of 1.98. What the model is assuming is something different from what stratification does. No longer are we breaking smoking into categories. No longer are we doing a separate analysis comparing males and females who don't smoke and males and females who are 1-pack-a-day smokers, 2-pack-a-day smokers, 3-pack-a-day smokers. Now what we're doing in a model is saying we assume that males and females have a log odds of disease that depends on their packs, but depends on packs in a linear relationship by having two parallel lines, one for males and one for females. And the gap between those two lines is the difference between a male's log odds and a female's log odds for any level of smoking, whether it be 1-pack-a-day smoker, a pack and a half, 2-pack-a-day, 2.5 packs, or 3-pack. The gap between those two parallel lines is the same. So now we're making an assumption that stratification doesn't do. It allows us to control for a confounder without having to break smoking into 4 categories. It allows us to keep smoking as a single variable, to represent it in a model with a single term, packs, rather than having 3 terms, packs 1, packs 2, and packs 3. That's going to lead to a smaller model. That usually means a more efficient model. So now we have another way of controlling for confounding in a model that we could not do with stratification. We don't have to categorize our confounder into different unique groups. We can keep it as a single continuous variable, but at a price of making an assumption of having a linear relationship. The model is also making the assumption that males and females have the same parallel line. Next week, when we come back, we'll talk about another type of model that doesn't make the assumption of linearity. It might be that of parallel lines. It might be that smoking does have a linear relationship to your log odds of disease, but maybe the slope of the smoking line for females is different from the slope of the smoking line for men. So no longer will we be assuming that we're talking about 2 lines, wrong direction, 2 lines that are parallel. And now we'll be talking about having 2 lines which are not parallel. Therefore, if I fix a level of smoking, non-smokers, 1-pack-a-day smokers, 2-pack-a-day smokers, and look at the gap between those lines, notice the gap is different. The gap is narrower if we're talking about non-smokers than it is if we're talking about, say, 2-pack-a-day smokers. So this model is allowing us to have different odds ratios for different levels of smoking. Instead of assuming that there's a single effect of males versus females, this model will allow us to estimate that males and females have different effects depending on the levels of smoking. And as some of an interaction term, what this model is going to include is a new variable, which will be the product of your sex status, male versus female, and your smoking level. And we'll pick this up next week and show how including this interaction term in a model allows us to have different effects of smoking for different effects of gender for different levels of smoking, different effects of smoking for different gender categories. So this is where we'll pick up next week when we talk about effect modification. But let me stop here. We still have a few minutes left. If anyone has any questions on anything we covered up to this point, in other words, up to the point of fitting a model, like the one I'm showing you now, or the model that we looked at right here, which assumes that there's a single odds ratio and controlling for a single confounder. Because looking ahead to next week, the other thing which we'll be talking about next week, and this is what I want you to think about for next week, I'll give you a homework assignment, is what if you have multiple confounding factors? So here's a model that has male in it, but also age, cholesterol, smoking, and blood pressure, simultaneously controlling for 4 confounding factors. Each of these confounding factors in this data set are continuous variables. You'd have to categorize them into 2 or more subgroups if you wanted to stratify by these. But now the model will allow us to control for them on the original scale by making assumptions of linearity, the assumptions of additivity. That's what we'll be reviewing next week, to get one coefficient of male